Let's learn how to completely understand the definition of a limit. A limit tells us what y value a function approaches as its x value approaches a particular value. Let's look at a quick example. Here I have a profit function where y is my profit in millions, and x is the number of tons of coffee I sell to generate that profit. My boss wants to know what value does the profit approach when our sales approach 2 tons of coffee. I can just plug in x equals 2 and see that y is going to be 6. Because this is a linear function, I know that the closer my x values get to 2, the closer my y value will get to 6. In other words, the limit of the function as x approaches 2 is 6. Now let's put it in proper notation. Here's the sentence I would write, and here's the mathematical expression I would write. Here's the general form. The number that my x value approaches is called a, my limit is referred to as L, goes on the right-hand side, and my function is depicted as f of x. Let's look at this graphically. The closer my x value gets to 2, the closer my y value gets to 6. So here's my profit function, here's my limit at y equals 6, which occurs at x equals 2. If I try an x value that's not close to 2, my y value is not going to be close to my limit. If I try an x value close to 2, my y value is going to be pretty close to my limit. Now let's go to the definition. Alright, let's say L is the limit of my function y as x approaches a. That means that when I test x values really close to a, my y values will be really close to L. How do we measure that closeness? We have 2 variables. Delta measures the horizontal gap between a and the x value we test. Epsilon measures the vertical gap between the limit and the y value, which we get from testing that x value. Here's the formal statement. L is the limit of my function y as x approaches a if for every value epsilon there is a value delta satisfying this expression. We're going to explain this expression in just 1 second. One thing to note is that delta and epsilon are gaps which measure distance, and since distance can't be negative, these variables can never be negative. They're always positive. Alright, let's look at the expression. We can see that the expression talks about the horizontal gap and the vertical gap. What it means is that for every vertical gap between the y value and my limit, there's a corresponding horizontal gap between my test x value and a. The difference, for example x minus a, can be positive or negative, but its magnitude must be less than delta. Similarly, y minus L can be positive or negative, but its magnitude must be within epsilon. Let's look at the previous example. If I test x equals 1.9, I'm going to have a horizontal gap magnitude of 0.1. Now, when I plug in 1.9 and I find my y value, I find that that's 0.2 away from my limit. If I test a different x value, I have a different horizontal gap, and when I plug it in, I'm going to find a different vertical gap as well. The size of my horizontal gap affects the size of my vertical gap. If there is a desired vertical gap, we can calculate how small the horizontal gap should be to make that happen. Let's go back to the example, which is an increasing graph. We can see that when we have a pretty big horizontal gap, we're going to have a pretty big vertical gap. When we have a pretty small horizontal gap, we're going to have a pretty small vertical gap. In this case, the difference x minus a gets less negative as my gaps get smaller. And the difference y minus L also gets less negative as my gaps get smaller. The differences have the same sign for an increasing graph. Let's look at a decreasing graph. Again, a big horizontal gap causes a big vertical gap, and a smaller horizontal gap causes a smaller vertical gap. Even though the differences have different signs, their magnitudes still decrease, and that means that the gaps still get smaller, like we said before. Now we can use limits to find these gaps. Let's go to an example. Our function is 2x plus 7. We know that the limit as x approaches 1 is 9. We want the function to be 0.1 away from 9. How far away from 1 should the x value be? In other words, if the vertical gap epsilon is 0.1, how small should the horizontal gap delta be? We're going to solve this by using the expression that talks about the gaps. To solve each part of the expression, we're going to drop the absolute value brackets, and we're going to switch the less than sign to an equal sign. We've been given epsilon, so we're going to start with that part of the expression. We know y is our function, we know L is 9, and epsilon was given as 0.1. So when we plug in our function, we can solve for x, and we can get that x equals 1.05. Now, we're interested in finding the horizontal gap, so let's use the delta part of the expression. A was given as 1, we just solve for x, and we can solve for delta. Do the same method and we'll find that delta equals 0.05, so our horizontal gap must be 0.05 or smaller. So the x value cannot be more than 0.05 above or below 1. Now let's look at some easy limits. The easiest is the limit of a constant function. The constant function is a flat line. It has the same y value for any x value. So the limit is going to be that constant number regardless of what x value we approach. For a linear function, if we want to find the limit as x approaches some number a, we can just plug in that number a for x. That's what we did for the profit function example. For an absolute value function, the limit of that function as x approaches a number a, all we have to do is just plug in that number a for x. Later, we're going to look at some more complicated examples of using the definition.